Hobby Lobby and it was really cheap. And my mom wanted me to wear it out of the house.
I'll take it.
No, I wear it around the house. I like live with it.
Yeah, same with mine. I like to wear my kids.
I like packages. You can pull more stuff.
Yeah, I know. I like to jersey. I usually chase them
I
and
also that I could use it after some because I'm going to be freezing. And it's so warm because it's black. So it's like something. It's so warm.
nice.
It's like the best thing I've ever done.
I'm not really wear that pink on Thursday. Sometimes wear that like blue one or the red one. Like the zip one. That's a good company.
He's still.
He's still
I wonder if he can live till the end of the year.
I'm always
Somebody will throw him away.
You think
All right, welcome everyone.
Oh,
Got a bunch of stuff to pass back to you. Should I do the sandwich one or the dessert one today?
dessert.
Okay, so attendance question, what is your favorite kind of dessert? You can think about that while I pass the stuff back.
Can you get my test or
I have all the tests graded.
okay, well you won't be handing
Including
out
yours.
anything.
So, lab reports as well. So pay attention to the notes I leave you on the lab reports. Those are always helpful. There are those of you who lost a whole bunch of points last lab report for something and then did the exact same thing again this one, even though I gave you a note about it. So read your notes. Okay. So,
There's not a lab report due today?
no, that was last class, right? Or is it is due today?
No, it's due Thursday.
Okay.
Thursday. I thought it was on your own.
I can't even remember where we are right now.
Thank goodness.
I know what I know what my lesson plan is, but homework wise, felt like an eternity this weekend. So on your tests, there's one question that the majority of the class missed, which surprised me because it was actually I didn't think it was that hard of a question, it was if there's a sample of oxygen taken in a certain layer of the atmosphere, or a sample of the atmosphere taken, sorry, and it's mostly oxygen, then what layer of the atmosphere would it be? Homosphere or heterosphere?
Atmosphere.
Yeah, it would be heterosphere. Why?
Because the hemisphere is mostly nitrogen and all that, and the hemisphere is mostly, I think, where is it? Helium or oxygen?
Yeah, so the heterosphere has two different layers that have different consistencies. But if it's taken, if a sample of air was taken anywhere in the homosphere, then it would be mostly nitrogen, not mostly oxygen.
Actually, I have my test right here.
I see, because I graded this scan copy.
I don't know. I was at Newark.
No, it's not too big.
What did you get on your lap for?
If you have,
I don't know.
you can turn in your stuff. I think it's the on your own questions, and if you have an early lab report, right? Is that correct? No, on your own questions, not yet. So if you have anything to turn in, you can turn it in to Mary Caitlin.
I guess I continue this one.
Oh,
So, what's the other one? Or were we supposed to check the oral questions?
Yeah. If you didn't check them, then go ahead and do that real fast.
I have a quick question.
Yes.
I looked at some of them.
I was confused on this too. So he said that the experiment did not fulfill the research question.
Yeah.
And he said it did show what happens to the can
What? I need to
when you
have
remove
one.
atmospheric pressure from inside of it.
And that is the research question: was what happens to a can when you remove the atmospheric
What did
pressure?
happen?
So it did suck up the water, and so
Okay.
you know, so that was a result. So that does answer the question. It's just not like, you know, and I didn't take any points off of that.
Yeah,
anyway,
no, I'm just trying to
but,
understand.
yeah. So we did show what happens, and even if nothing had happened, that would have been our answer. You know, it just wasn't what we were expecting exactly. Yes, Dylan.
Something that happened, I noticed that I read like in the book the can was supposed to crumple.
Yeah.
And would you say in like your lab report like it was supposed to, or did you say what happened?
I mean, one person, I think it was Jake, wrote that the book said that this should have happened. However, this happened. That's fine. He can do that if you want. just, it's good to cite the book, actually say like the book said this rather than just like it was supposed to, but, it's fine if you do that. I think that, was actually really good on James for, Jake. Handle that.
Yeah, I've never been. I never.
We should have the middle one, but I forgot that one. Are you like cold in here? Cold, give me
So, on your lab reports, we can take a look at them. Take a look and see if you had excellent written next to any of your sections. And I'll take a moment for you guys to have a chance to share, read your section if it was marked excellent. So what about in the results? Who had excellent on their results?
Very good.
Yeah, I have excellent on my
Okay.
results.
Can you read your results?
Sure. All six cans steamed on the griddle. Each of the 5 cans that were placed upside down in the bowl filled particularly with water, but did not crumble. Nothing happened to the cans that was placed upright in the water. This was the control for the experiment.
Okay, good. So did she address both parts of the experiment, the control and the other tests? Yeah, and she made it really clear which was which when she was talking about them. If you just say something like the can filled with water, I would say, which can, was it in the control test or the regular test? And was it just one or was it a different number? So she gave the number of cans. She said what she saw. She made it clear that she was reporting based on the normal test, not the control test. And so it was very easy to understand what she was talking about. Remember, you're always writing from the perspective of pretending that the reader has no idea what your experiment is and you're explaining it to them from the ground up. Yes?
Did y'all have an extra credit question?
Not on the test, no. It was, but you guys did really well overall. If you check the averages on Praxis School, you might see a low average, but that was because the 2 lowest scores were much lower than the other ones. Everybody else got an 89 or higher. So, so anyway, I was impressed. And I think there was 100 or 2. But okay, so next section, the after the results, I am blanking, the discussion. Yeah, who had an excellent written on the discussion? Can you read yours?
Okay. Our control experiment did exactly what it was supposed to do according to the tests. When we heated the cans on the burner and the water turned into steam, it released the atmospheric pressure in both. However, the steam exerted pressure so the cans did not crumble. When we placed the control experiment can in the water, nothing happened because the steam turned into liquid and air rushed back into the can, renewing the atmospheric pressure inside. Our variable experiments did not go exactly as the text or our hypothesis said it would. The text said the cans would crumble because when we placed them in the water upside down, the steam would turn into water. But air would not be able to rush back in, and due to lack of pressure in the can would crumble. However, the text did say that the can was capable partly of water because of the pressure in the water, and that did happen in our experiment. So our experiment technically went well, but our hypothesis was correct.
Very good. Okay, so I liked a number of things about that. What was good about that? It's very descriptive, yes. What else? One thing is that it really kind of wrestled with the conclusions that were being drawn. It wasn't just saying our hypothesis wasn't right, so the whole thing was a failure. It was saying our hypothesis was incorrect, but we still saw the effects of the pressure, causing the water to rise in the cans. And I like that she also quoted the book in it, which is not required, but the way she did it, I thought was really good. Well, basically saying we didn't see this result that we were expecting from the book. However, the book did explain this result, which was the water going up. And did she kind of give an explanation for why each part of the results actually happened? Yeah, she explained, scientifically why each one happened. If you just kind of say why it happened in the results and then you don't give an explanation down below, you're not getting as much value out of the experiment. So that was really good. And what about the conclusion? Somebody get an excellent on the conclusion. Mary Kate.
This experiment was conducted with multiple possible sources of error. There were multiple cans all put on the burner at the same time, but the cans were all open a different amount. Also, the griddle being used was pretty old and cheap, so there may have been different spots where it burned hotter versus colder. We waited until there was steam coming from each can until we used one of them. This means that some cans that had steam coming from them before the other cans were not taken off immediately. Another possible source of error is that we poured too much water in each of the cans, and they did not have the same amount of water because we did not measure. According to the textbook, the more water we use, the less dramatic the effect. The cans we used were root beer cans, and since there are so many chemicals in root beer that may not have been washed out of the cans well enough, they could have affected the results. I conducted this experiment at home, and the moment the top of the can was dipped in water, it crumpled inwards immediately. Because of this error analysis and the results of my attempt, we must have done something wrong in class in order for it not to work.
Very good. So mostly what I liked about, what would you say would be the main thing that stood out to you about that?
She did it at home.
But that's one thing, yes. And she was absent. You guys don't have to. But yes.
I just realized there's more on the back.
Okay, please read it.
Okay.
Oh, and there was a diagram too. That was good. Drawing it.
We could have improved this experiment by using a different griddle and pouring less water into the cans. We also could have widened the openings of the cans that were not open very much. The griddle we used had been used for many years prior and was bought for a cheap price, so the heating throughout the griddle may have been inconsistent. It was mentioned that the griddle was even slowly melting its own plastic parts.
Yes, very good. So it was really thorough. There was a long list of possible errors and means for improvement. You know, it was very thoughtful. So like she actually thought about like all the different ways that it could have been improved and all the different problems that occurred in it. And I really do wonder about, I wonder if I just, you know, if I can find cans that are thinner, you know, because like if you get certain brands, they have thicker cans, that may have been part of the problem. But maybe, I don't know, maybe like next year I can just get an assortment of cans or something. Although that would be hard for me because we never drink any soda. But anyway, so yeah, that was very thorough. Let's do one other of those. Anybody else get excellent in their conclusion section or whatever it's called? I'm sort of blanking on everything. Yes.
I did.
Already called
Somebody
it.
else did it. They were there because I did that.
Well, you two of each.
Yeah,
So
we were red.
pick a number between 1 and 10.
5, 6.
You were closer. It was a 4. So you can read
Yeah.
yours.
Conclusion. Okay. Atmospheric pressure is all around.
Pay attention.
And is exerting pressure on everything. An ordinary empty aluminum can does not crumble on its own under normal circumstances because the atmospheric pressure outside the can is equal to the atmospheric pressure inside the can. In this experiment, we lowered the atmospheric pressure inside the can by boiling a small amount of water in them.
I'm going to pause you for just a second. So I liked in the beginning, she brought it back to the kind of the bigger issue of like, you know, atmospheric pressure, reviewing the fact that, you know, this experiment is about atmospheric pressure and there's atmospheric pressure all around, without and within, and that's why cans normally don't crumple. So that was a really good, helpful explanation that brings it back to our purpose. So continue.
The steam forced the air out of the can. The steam forced out the air. When we sealed the can by holding them upside down in the water, the can did not crumble, but that did fill a particular with water. The can acted as a barometer. The atmospheric pressure on the water in the bowl was pressing down on the water and forcing it into the vacuum we had created in the can. Possible sources of error include uneven heat from the griddle, unequal amount of water in each can, and water and ice in each bowl. Some of the cans may not have been rinsed out thoroughly as others. In addition, to correct these errors, test each can individually instead of all of them at the same time may improve the experiment. Another possible improvement is the second control, can which just as the water covering the bottom of the can, but is not heated. When this can is placed upside down in the water, it should not act as a barometer and have water forced from the bowl into it because the atmospheric pressure should be the same inside and outside the can. This experiment was interesting because our hypothesis was not supported by our result. We had to consider another valid result, then the can acting as a barometer.
That was good. So one thing I liked was at the end she pointed out what was actually like interesting to her about it, and she pointed out that while it wasn't the result we were looking for, basically there was still an interesting result, which was the can acting as a barometer, which kind of helps us fulfill the purpose. So yeah, that was really good. Again, very thorough look at the error analysis. And one thing she pointed out was a very simple one, which is we only did one control test. What if we had done more? And you can always improve by doing more tests. So actually, here's an interesting fact about that statement I just made, that you can always improve by doing more tests. Did you know, if you have a random jar of like jelly beans, any amount, this is something that one of my, it was basically a statistics professor, but it wasn't quite called statistics. It was just like using statistics in political science. But I can't remember the title of the class. Anyway, he said, you got a big jar of jelly beans and you ask, one person to guess the number of jelly beans in the jar, it's probably going to be pretty inaccurate. You get 100 people and you average their answers and it'll get more accurate. You get 1 million people and average their answers and it'll be really accurate. You get like, I don't know, 2 million people, whatever, it's even more accurate. And basically, oddly enough, if you were to just take any people, and just the more people look at it, kind of the more tests, basically the more surveys of how many jelly beans you think are in there, then the bigger your sample pool, the more accurate your number, until once you get to a certain sample size, it'll be pretty much exactly right. Isn't that crazy?
That is crazy.
Yeah, and it doesn't depend on the intelligence of the people necessarily. I mean, when you average with a large number, then you're going to get a good, you're going to get some people who are way off this way, some people who are way off this way, and the average ends up being accurate. Yeah, actually, like the more times you test something in a similar way, the more accurate your results will end up being on average. And same thing with like, surveys and stuff like that. There's going to be a lot of polls for the elections and stuff like that. Look at what actually like is the process for getting those results. Because if they say 10% of, only 10% of people are, I don't know, candidate A supporters. But what if you only sampled 10 people and you only sampled them from a nursing home in Miami? And, and those people of a certain, age demographic, maybe they're the same, they're all men, maybe, basically it may just be that you have a very small, not very diverse sample size, and that'll yield an accurate result. Whereas if you had a survey that said only 10% of candidates are voting for, or 10% of people are voting for candidate A, but you had 1 million people of all different demographics and across a wide area in the US, would that be more accurate? Yeah, definitely. So if I haven't said it yet in this class, Mark Twain famously said, have I given you this quote yet? And I'm going to give you the G-rated version of it, but he said, there are 3 kinds of lies: lies, darned lies, and statistics. Meaning that if you use improper surveys, or not enough surveys would be one thing, or if you just simply twist the data, it can actually be really deceptive. More than lies or darned lies, I guess. So anyway, moving on. I'll finally take attendance, just for fun, really. So at this point, I know who's here. So, favorite dessert. Oh, and just so you guys know, I figured out the issue that I was having with Zoom, and it's an issue that other people were having too. If you go in through the links, then it doesn't always let you in. And in my case, it got to the point where for some reason it never let me in. But if instead you go to, you log into Zoom and you go to join meeting, you guys should have received an email at some point giving you like a meeting ID for all the classrooms. But even without that, what the meeting ID is it's the name of each classroom. So for example, this one, you go to join meeting and then you all lowercase, one word, you use the meeting ID kids praise, because that's the name of this room. Or if you're in my logic class or guitar class, then you would use That's the We Worship room. So you just type We Worship, and that'll take you right in. And it's worked for me every time. So the other thing is I went ahead and just since some of our more recent videos have had a lot more like footage of students, I went ahead and made all of our videos unlisted, but you can access them if you have a link. And so when you're absent, I've been emailing everybody who's absent a link to the video. I'm also, after class, usually before 5 p.m., I'm posting the links to the lesson plans on Praxis School. So you can always go back and re-watch class, except for like there's maybe 1 or 2 days where like just nothing worked technologically, and we didn't have a video, but anyway, you can plan to do that if you ever need to. And if you're unsure what happened in an experiment, go back and watch it. You know, we don't always have the best footage, and sometimes you don't see that much of the experiment, but you'll at least hear what we're saying about it. Or you can do it at home. You know, again, most of this stuff is made up of, most of the supplies are trash, more or less. And I collectively refer to all of mine as my science trash. I remember when I was like, I used to do a similar class for CC, but it used the same book. When I wasn't doing CC anymore, I said to my wife, guess what? We can get rid of all my science trash. And then they're like, hey, can you teach science with this book here? And I was like, oh, we're keeping the science trash. Anyway, attendance. Annalise, favorite dessert?
Ice cream.
Any particular flavor?
Chocolate ice cream.
Nice. It's good when your favorite is something that you can just get anywhere. Bo.
Couche's beignets.
What?
That sounds good. It's like a powdered sugar donut, sort of, but not exactly. It's a Louisiana thing. Bryson. Spaghetti. So my uncle ordered some kind of a meal at a Mexican restaurant, actually in Mexico, and he didn't know what he was getting. Turned out it was chocolate spaghetti. But it was probably like mole, which is like a savory sauce made out of chocolate. I never asked though. But Caitlin.
Probably like pound cake.
Nice. Dylan. What kind of ice cream? Mint. Nice. You can actually like it's kind of like a personality test to figure out what people's favorite ice creams are. There's different articles I've read about that, and mint chocolate chip is always one of the categories. So Jake. Napoleons? What are those?
So it's essentially like a cream puff, but it's just longer and covered in chocolate.
Oh, I think I've seen those.
And James.
Probably Dairy Queen Blizzard.
Nice. Kate.
Chocolate cake.
Nice. Mary Caitlin.
Mint chocolate chip ice cream.
So, whatever it says about that, you guys have in common, I guess. Rory. Oh yeah, she's absent today. Yeah. And Sarah.
Carrot cake.
Carrot cake. Nice. Yeah, you can get really good carrot cake. Like it's done right, it's amazing. Vale.
Cheesecake.
Nice. Yes, very good. I kind of don't really like desserts as much anymore because we don't really do too much like normal dessert type things. My wife uses a lot of stevia and then I just never touch it because I hate stevia. So, but sometimes she'll make additional batches of things for me. But you know, they're not really desserts, but I really like sesame balls. And so it's like dough wrapped around carob, which is kind of tastes like chocolate, but it's actually like some other kind of a bean. And it's sweetened. And then it's like fried in sesame oil and like rolled in sesame seeds. But also cheese wontons. I'll count that as a dessert. And I like them both from the same restaurant, especially Tan's. How have you ever been to Tan's Asian Cafe? That's like probably my favorite restaurant. If it's not my absolute favorite, it's one of them. Although my favorite type of food is Thai food at this point. I really love Thai food. We actually made some curry a couple nights ago. It was really good. Okay, So let's jump into the module. We've already talked a little bit about the main thing you need to understand about water. And what is that?
It doesn't hold, like it doesn't make things float.
So we talked about the surface tension. And surface tension is the result of something else about water. What's its most basic characteristic we were talking about when we talked about cohesion and surface tension? What do all those things come from? Quality of water that starts with a P.
Sure.
Nope.
Proton.
Nope. All right, so this is going to be polarity. Yeah. I'll just say polar. A polar molecule this isn't the actual definition, but this is just me paraphrasing the idea. It's going to have an imbalance of charges. And in the case of water, got a big oxygen, little hydrogens, and what causes, which side is going to be slightly negative and which side is going to be slightly positive?
The big one will be negative and the small one will be positive?
That's right. Why? The book really simplifies it by kind of just saying it's like a tug of war between this side and this side over the electrons. And so I gave you more information in the book by saying that as the electrons are orbiting, this is bigger. So there's a bigger circumference that the electrons have to orbit around on this side. So at any given moment, the 10 electrons that are in this molecule, more of them are going to at any given moment be on this side than on the other. So even though, like, what is the actual charge of water overall? Positive, negative, or neutral? Phone away, please. Phone away, please. Thanks. Say it again. Nope. So it's made of atoms. What are the charges?
Is it going to be neutral?
It's going to be neutral, yes. So overall, it's neutral, but there's going to be more negatives hanging out on this side at any given moment, more electrons on that side and fewer on this side. So you still have 10 protons, 10 electrons in this whole thing. So that's 10 plus 10 because of the protons, minus 10 minus the electrons, or plus the electrons because it's plus and negative. And then the result is zero charge, but it's polar.
So in the book, it said the negative is -8 and the two positive are +8.
Yeah.
But there's two positive 8s. How come it cancels each other out?
It's going to be because there's actually only one positive 8 because there's this is the one that has 8 protons inside. So you got 8 protons there, and then these are going to be 1 proton each. So that's 8 plus 1 plus 1 is going to be plus 10 protons in total. But then each one, like each proton comes with an electron. And so the 8 oxygen protons will be accompanied by 8 electrons that come with that oxygen atom. So then it's going to be 8 electrons plus 1 electron plus 1 electron. So does that make sense?
Mm-hmm.
Is this where you could also just explain the net, whatever that word is? Net,
Charge, right?
Yeah. Electrical, whatever.
Yeah, so the net electrical charge is 0, but there is a slight positive charge on one side and a slight negative on the other because out of that 0, it's kind of like this. Let's say that you have, chocolate and vanilla ice cream. You can have it like in a carton. And have you ever gotten a carton of ice cream where it's like, let's just say this is a bird's eye view, you're just looking at the top. one kind of ice cream I really want to try, which is mango habanero. I found that at Walmart. I'm gonna buy it. So left is chocolate, right is vanilla. So if you took a scoop exactly out of the middle, well, let's say that you have this kind of chocolate and vanilla, all right? And then you have another chocolate and vanilla, but it comes not separated, but swirled. All right, so let's say it's still 50% chocolate and 50% vanilla in both. But in this one, let's say you take a scoop out of this one. This would be like your nonpolar molecule, because when you take a scoop of it, let's say that the vanilla represents the protons and the chocolate represents the electrons. If you take a scoop of this, wouldn't the electrons and the protons, the chocolate and the vanilla, be evenly mixed together? Yeah. But let's say you take a scoop right out of the middle of this one, exactly in the middle. Would that still be 50-50 chocolate and vanilla? Yeah, so we could ask, is this more chocolate or more vanilla? Neither. It's neutral. There's not more positive or more negative. It's just neutral. But would one side be positive and one side be negative? Yeah. So the net charge, the net flavor of this one is not chocolate nor vanilla. It's both. And so if this were like representing, a polar molecule, it's kind of like how with a polar molecule, the net charge, the overall charge is 0. It's not positive or negative, but it's got a positive side and a negative side. Does that make sense now? Okay. So that's how water is. Positive side and negative side. I really want ice cream now. I normally don't. But talking about desserts and then that. Okay. So real quickly, there's different things that happen that we've done to water in our experiments. Let's say that we're doing electrolysis. What do you call this little bar that is drawn there?
Is that the electrical bond?
Yeah, so this is going to be your chemical bond. And very good. So I'm going to go out of order just to make something really clear. So those are chemical bonds. Do they really look like a stick?
We don't know.
No, yeah, it's what it really is it's a bond between the electrons and these and these. So if the electrons are orbiting around from one atom to the other, then there's going to be a chemical bond. And so when we performed electrolysis, what happened remind me, what is electrolysis?
Electrons.
Breaking down of a molecule.
Yeah, we're breaking a molecule down using, yeah. So when we ran water, or a current from the 9-volt battery through the water, what happened is the electricity severed these bonds. And that kind of makes sense because it's an electromagnetic thing going on when the electrons are orbiting. And so then you add more electricity and it can upset, whatever balance is causing the orbit to go on. So we're splitting not atoms or anything like that. We're just splitting the atoms apart from each other. So we're separating the atoms in the molecule. So when we did electrolysis, what we're doing was we're breaking the chemical bonds. And what escaped? We had hydrogen on its own and we had oxygen on its own. All right. Now, is that what happens when evaporation occurs, when water evaporates? No, I saw a head shaking no. What do you think happens then, Vale, or do you have anything to add?
When I shake my head, I was just using common sense with that.
Any idea, just kind of on a common sense level then, and anyone can answer this, why would you assume that this isn't happening when water evaporates? Yeah.
It's still a form of water.
Exactly, yes. Is that kind of why?
Yeah.
Yeah, because it's water vapor, right? It's not oxygen and hydrogen. And so what's happening there is there's another kind of a bond that's being broken by heat. And we've talked about heat. There were some points lost on stuff about heat on the test, but most of you guys got it. So when water is in liquid form, there's a weak bond. It's not as strong as the chemical bond, but there's a weak bond that occurs between water molecules. And it's because of the polarity. It's where the negative end attracts to the positive and the positive attracts to the negative. Because remember, this side's positive, this side's negative. So we got positive, negative, and if I drew more, you know, we'd have more positive and negatives connected. I guess I'll draw one more, just for the heck of it. So what we have here is purple hydrogen bonds connecting these. And so the hydrogen bond is the type of bond that isn't connecting atoms to each other to make a molecule. That would be the chemical bond. The hydrogen bond is when you have two molecules with hydrogen in them, where a positive end is attracted to a negative end, and that's going on with water. And so what's the result of this hydrogen bonding? Like, what's going to happen to the thickness of the water, the density of the water, as a result of hydrogen bonding? So you're going to get more dense or less dense? Other way down, more or less? More dense, yeah. This is actually why I mentioned before that water is more dense as a liquid than as a solid, because when water can flow, then this hydrogen bonding can occur. They're not locked in place as a solid, so they can get really close to each other as they flow around. So when we apply heat, what is heat again?
But it's like the, yeah, I know.
Energy that is transferred as a constant change in temperature.
Yeah. So it's going to be energy transferred as the difference as a consequence of temperature differences. And so like when you are, but remember like the heat of something, like its temperature is going to be the result of the molecular motion, right? So as these molecules are getting hotter, they're vibrating if they're in a solid, or if they're in a liquid, they're flowing farther apart because they have more energy. And if they're a gas, they're just spreading farther and farther apart. And so what we have then is with the heat, we introduce heat, and that's going to break the hydrogen bond because it's going to add enough motion to these atoms that they're going to break apart. So it's kind of like if you had like, I don't know, 3 of you and you were linking arms in a line, or all of you, if you're all linking arms in a line, and then, I don't know, you started like waving your arms like that, wouldn't there be a certain point if you just increase the force of the wave where eventually your arms are going to come apart from each other? That's what's happening when you're adding heat to water. You're adding motion to these molecules until they get enough motion going on that they break apart from each other. And so that's how evaporation occurs. So in the experiment with soda cans, like that's how we got the boiling to occur. Like we add heat to the water, and then that converts it from a liquid to a gas by breaking the hydrogen bonds between the water molecules. And then each of these would evaporate. You know, they would spread apart and come out as steam. So water vapor. There's still water. There's still whole water molecules, unlike when we did electrolysis and we get oxygen and hydrogen separate. So they're water molecules, but they're a gas now. So any questions about that? All right. So make sure you know the difference between hydrogen bonds and chemical bonds. And which one is harder to break, a chemical bond or a hydrogen bond? It's actually the chemical bond. The chemical bond is stronger. So when we're applying electrolysis, we're doing something that's a little bit more, you know, I guess invasive or whatever, than, you know, we're breaking a stronger bond through electrolysis than we are just by adding heat to break the hydrogen bonds. All right. They introduced the idea of chemical formulas, or formulae if you're, you know, more picky about your Latin. And studying Latin messes you up because it's like you realize everything you pronounce is wrong. And like our plurals are often wrong and things like that. It's actually why I say libertas and everybody else says libertas, is because I've taught Latin and I know that in Latin the word is libertas. Yeah. Sure. So real quickly, chemical formulas. What's a chemical formula that we're already using a lot?
H2O.
Yep. So what does the first letter stand for?
Hydrogen.
Hydrogen, yep. What does the 2 stand for?
2 hydrogen.
Yep. And then what does the O stand for?
Oxygen.
Yep. All right, what if I have something like this? I'm just going to make something up. What would that be?
4 helium and 1 oxygen.
Very good. 4 helium and 1 oxygen. So how do we know that this is not helium and then some other element that starts with an E? Yeah.
Because what capitalized is the element, and then there's another one that will. There's another word for it.
You always capitalize the first letter of the element, and if
Yes.
there's a lowercase, it's still part of the element.
Exactly. So you only get a new element when there's a capitalized letter. So if I have something like this, again, these are not real chemicals. If I'm remembering all these correctly, that's an L, a lowercase L, not an I. So tell me all the different, how many different, you know what, maybe I'll make it a little bit more complicated. I'll add some stuff. All right. So how many different elements are there in this molecule, which is non-existent? Okay, let's find out.
9.
I hear 6. I hear 9. How many?
Oh, different one?
Yeah, different ones, different atoms. All right, so we have, because you start a new one with every capital letter, is how you count them. All right, so that would be what?
1. So like
That's 1. That's helium.
Isn't there 6 different molecules?
And then we have,
4.
yep. So this will be.
I thought that was a Y.
Oh yeah, that's
I
4.
did too.
That's a sodium. So and how many sodiums would there be?
4.
4. Yeah, 1 helium. And if it's just one of something, you don't put a number. You only put a number if there's 2 or more. So 1 helium, 4 sodium,
13.
1 sulfur,
2 oxygen.
2 oxygen,
1 helium.
1 hydrogen, and what would this be? I'll be impressed if somebody knows what it is off the top of their head.
Mercury.
Nope. Unless I just did it wrong. Where's PL? Is it plutonium? I think that one is PU, but I could be wrong.
No, I don't see it.
Or just P, I can't remember.
PU.
Okay,
Yeah.
it's PU, plutonium.
I don't see any.
Yeah, it's only P.
Okay, maybe I was just wrong. Maybe there's just P. What's just P?
P is palladium.
Phosphorus.
Okay, phosphorus. Great. I was going for lead, which what's the formula for lead? Because I know in Latin it's plumbum.
Your PB.
PP? PP. Okay, there we go. Thank you. I'll do that. Yeah. So that's one that just think a plumber using lead pipes because they used to, and so then the term plumber came from the Latin word for lead, which is also where this I guess it would be like plumbum.
So what's the thing again? PLP.
So PB is going to be lead, as strange as that sounds. All right, so then, yeah, we have a few different elements, and actually, I could ask the question a couple ways. I said how many different atoms, and so first I'll ask how many different elements. 1, 2, 3, 4, 5, 6. Now, how many different atoms?
13.
13, you say? So we got the 6, and then we have 4, so I'll add 3 more. 7, 8, 9, 10, 11, 12. I got 12.
Wait,
What?
Yeah.
1, 5,
So
8,
1,
10. Yeah, you're right.
So
12.
3, 6,
4, 5,
7,
6,
8,
7.
9, 10, 11, 12. Wait, that time I counted different.
1, 2, 3, 4,
1,
5.
2, 3. Okay, 1. So 5, 6,
6,
8. There we go. 9, 12.
12.
It was 12.
12.
My first and third counting were correct. All right. So yeah, that's the basics of the chemical formula. It's kind of easy once you get it, really, because there's only two things to remember. One is the numbers and how they work, and then the other one is just how the lower cases work. But they're not a new element; it's only the upper cases that are new elements. Now, are there any three-letter chemical formulas or symbols or whatever?
Yes.
Yeah.
Like what?
Wow. I can't even say that word. Like U, and then U, N, U, B.
So there's U is
And
one.
then
I don't know.
That's interesting. Yeah, but most of them are either just 1 or 2 letters. And I'll point out something interesting that as we've added elements, he points out that by the time you read this book, there may be more than are on this periodic chart at the time of publishing. But at this point, if we ever make any, like if we ever find a new one, it's because we've created it, not because we found it in nature. So you can, put things in a particle accelerator and like collide them and make different combinations to result in like different reactions that'll result in forming new elements. And I imagine it's probably pretty hard to do, but when that happens, they only exist for like a split second because they're not stable. So any of the newer ones are probably going to be like not very stable. All right. So let's move on. We've already talked about chemical bonds, water's polarity. And remember so we have 3 types of substances that we need to go over, 3 categories. We'll talk about water as a solvent. Change of color. Polar has an imbalance of charges. Like the scoop out of the middle of the half chocolate, half vanilla. Non-polar substances are going to have just basically balanced charges. So in other words, the protons and electrons are going to be more or less evenly distributed. So you don't really have one side that's going to act like a magnet the way water does or any other polar would. And then we have ions, or if you have a bunch of them together, maybe ionic compounds. And these are going to be like positive or negative. These actually are charged, because remember, if something is an atom, does it have a charge? Nope. If you have a molecule that's only made of atoms, then would it have any charge? Any net overall charge? If you have a molecule that's only made of atoms, would it have a charge? It wouldn't, because it's kind of like, if you have 0 charge for all of your different atoms and your molecule is made out of like, let's say H2O, for example, hydrogen has a charge of 0, oxygen has a charge of 0, and I'll do another hydrogen. What happens if you add 0 plus 0 plus 0?
0.
Yeah, so no charge. So molecules are not going to have charges. Overall, they might have, a slightly positive or negative side, if they're polar. But if it's just an ion is what we call an atom that's lost or gained an electron or proton. Basically, and I don't know, in normal circumstances, you would really have things losing protons, but you do have things losing electrons. It's actually pretty easy to lose an electron. Even just rubbing against something else can cause electrons to be lost, and that's what generates static electricity. So ionic compounds, these are going to be substances that are positive or negative. So let's open up your book real quick. Let me know what page, if you get there before me, you see sodium chloride. That's an ionic compound. There we go, page 92. All right, so what you have on page 92.
Can I ask a quick question?
Oh yeah, sure.
You wouldn't have a molecule that wasn't made of six atoms, right?
I don't think so, because at that point you wouldn't call it that.
Yeah.
So you have, this is actually like sodium chloride is called table salt. So it's a combination of two ions, and we're going to talk about why it dissolves in water. We have the larger chloride ion. And so it's made out of chlorine, but it's an ion. So it's charged negative. And then we have the smaller positively charged sodium ion. So what you need is you need not just like chlorine and sodium, you need specifically a negative chlorine ion and a positive sodium ion. And together they make salt, table salt. And remember, do charges attract or repel each other? So if you have two negatives and two positives, will they attract or repel?
Yeah.
Repel. And if you have opposite charges, will they attract or repel?
They attract.
Yeah, so if you had a whole bunch of sodium and chloride together, then how would they end up building into a structure? Would it be sodium and sodium and sodium all on one side, and then chloride and chloride and chloride all on another side?
Maybe like sodium chloride, sodium chloride.
Yes, exactly. So it's going to mix. So the result is table salt. It's built into structures like, well, yeah. This will take me another moment. There we go. So that's table salt, sodium chloride. So that's going to be an example of an ionic substance. Now, let's see how water actually dissolves this. It turns out that water can dissolve anything that has a charge. What do we mean by dissolve? Any ideas?
They kind of combine.
Now they combine, that's good. If you have a solid mass of salt and then it dissolves, what's actually happening to it?
It's slowly coming apart.
Yeah. And what's really happening is like all of the matter in it is getting kind of surrounded by, like you don't really think of it this way, but it's getting surrounded by usually water. And so that instead of having a big mound of salt, you have all the salt spread out so thinly among all the water that you can't actually find the salt anywhere in it. Like something is dissolved when you basically just can't find it. It's been spread out so thin, it's like you can't even see it there. So a solvent, give me a definition of a solvent, please. To the book.
Solvent is a liquid substance capable of dissolving other substances.
Very good, thank you. Liquid substance capable of dissolving another substance. People sometimes refer to water as a universal solvent or a near universal solvent. It's not totally true, but it can dissolve a lot of things because a lot of stuff has a charge. So water can dissolve anything polar. Sugar would be an example of a polar substance. And it can also dissolve things ionic, like table salt, because these will have either a charge overall, like these have a net charge, these don't have a net charge, but they will have an imbalance of charges. And if one side is slightly positive or negative, then it'll attract water. Non-polar would be stuff like oil. It's not going to be dissolved by water. It doesn't mix. All right, so what's a solute? S-O-L-U-T.
Solute is a substance that is dissolved in a solvent.
Very good, thanks. So they kind of, you can't really define this one without that one. Substance that is dissolved by a solvent. There we go. Now, so water is going to be this. If we were to mix water with salt, which one is the solvent and which one is the solute?
Water is a solvent, solid is a solvent.
Very good. All right, now I'm going to draw that happening. Here is water molecule. And so the chloride is negative, right? So that means the positive side of the water is going to grab on to the chloride ion. And so it'll actually, if the chloride ion is more attracted to the water, which it will be, than to the sodium, then what do you think will happen?
It'll break apart.
Yeah, it'll break the bond with the sodium, and then these two are going to move apart. And so this water molecule just stole that chloride ion. And then let's say that one's taken and another water molecule comes over here. Which side, the hydrogen or oxygen side, is going to attract to the sodium, the positive sodium? Very good. Because that one's more negative overall. So wrap those up in a shared bond, and this one will pull that one away. That's how dissolving actually works, believe it or not. And so why do you think it would be helpful to stir salt and water to make it dissolve faster? No going to sleep, please. Thank you.
Because when you stir it, then it helps the water to grab it, I guess.
Yeah. So if you're stirring it around, then the stirring can actually kind of break up the structure some. But the more surface area, like the more water you have exposed to the surface area of this, including like if you break this apart, you're making more surface area for water molecules to get in there and attract to the different particles. And so that'll make it dissolve faster. All right, questions about this? And water will dissolve all kinds of different things that way. So
Except for oil.
real quick, yeah, so out of polar, non-polar, and ions, what kinds of substances will water dissolve and what kinds will it not? Someone, let's see, maybe James. What kind of substances will water dissolve?
Will water dissolve or will dissolve in water?
Either one.
Okay, I guess gas, gas, because in the water, can dissolve.
Well, what were the three types of substances I was just talking about?
Polar, non-polar, and ion.
Good. So out of those, which ones will dissolve in water?
Polar.
Okay, polar. Good. And what else?
And non-polar.
Not non-polar.
Oh.
Polar and ions. All right. And Dylan, why will polar and ions dissolve in water when non-polar will not?
So because the like opposites like attracted, like water attracts with the negative and the positive side.
And so in the case of the polar, why can't it do that?
Why can't like water break down for it, or?
Yeah.
Because it's not negatively positively charged.
That's right, yeah. So the charges, the negatives and positives are so evenly distributed that the water doesn't grab onto one side of anything. You know, it doesn't grab onto a positive or negative particle in it because they're all just mixed. All right, so we've covered a lot of the module. There is more. But really, if you have a good understanding of that, like everything in this module makes sense if and only if you understand water's polarity. So if I explain water's polarity once for one application, you kind of get it for everything. We talked about hydrogen bonding a little bit, so maybe I'll finish that section up. Again, what is hydrogen bonding?
Is it when two hydrogen, H2O molecules are the positive side of one is attracted to the negative side of the other, and it creates a weak hydrogen.
Very good. Yes, thanks. And so, yep, and that's going to be what results in things we'll talk about next class, which is cohesion and surface tension. But we already talked about those. So, okay, thanks very much. I will see you on Thursday. Thank you. Where's the what? Over there, please. I'm good. You too.
I'll be in the hallways and